Hi, so we are going to talk about how to do single rotation in general for an AVL tree. So far we have done quite a few rotations, both singles and double rotations. Now, all of them, if you haven't noticed, they all occur at the very bottom of the tree. Now, that's not necessarily always the case, as sometimes rotation can happen higher up in the tree, and that it would be the general case. So let's look at an example. Let's look at this tree. The first question is when you see an AVL tree is, well, when you see a binary search tree is it an AVL tree? So think about it. Is the original tree without a one, is that an AVL tree? And then now we're going to be inserting the number one in there. And after the insertion, ask yourself, is it still an AVL tree? And if it's not, uh, where does the imbalance occurs? And if there are multiple imbalances, where is the one that you want to fix? And remember what we said, we want to fix the ones starting from the bottom up. Okay, so the original one is an AVL tree without the one. Okay, now after we insert the one, then it's no longer an AVL tree. The imbalance, the first imbalance, actually, I think the only imbalance that's in this tree really occurs in the node 5, where the right subtree is height 0 and the left subtree is height 2. So the difference is 2. Um, Now this is starting at node 5. This is going to be the left case. And why? How do we know it's the left case? Well, you look at the left child, left subtree, and the right subtree, the height. The left subtree is higher, right? So that means the imbalance kind of occurs on the left subtree. So that is the first left. And then you go down one level, come to 3, and you look at the right, the left subtree and the right subtree. Well, the left subtree is higher, so we will be going down another left. So this is the left case. Okay, so what do we do in the left case? Now this is slightly more complicated than our the previous left case that we saw, because now all of these nodes 5, 3, and 2, they have something hanging off them, right? It's no longer just all by themselves. So the good thing is we can mostly ignore them, because for example, anything that is in the right subtree of 5, we're not going to change anything in there. If there are many more nodes in there, well, they won't, in this case, they're not, it only has one node, A, right? Imagine there are more nodes in here. We're not going to change any of them, because, remember, if we do a left, if we handle the left thing, we only change one edge. Okay, so we can kind of just denote this whole part as, a subtree in a triangle. In this case, it looks like a tree. And then the same thing for the right subtree that's hanging off 3. We are not going to change anything inside that subtree. So let's represent that whole thing as in the little triangle. And kind of the same thing here. Remember, the only edge we're changing is this one, right? So we're not going to be touching this edge or anything that's in this subtree here, which is denoted by X, and this subtree is denoted by Y, and the subtree is denoted by Z. And now we are going to rotate this tree to the right. Now, if you remember what we did in the simple case, we'll simply put 5 as the right child of 3. And that's exactly what we'll do here. We simply take 5 and make it the right child of 3, and everything else is the same as before, right? Even the same for the subtree Z here is still attached to 5. Now, the only odd thing here is that there are the number 3 now has 2 right children, because we attach 5 to it as the right child as well, in addition to 4, or the subtree Y. So how do we fix that? That's not good, right? That's no longer a BST. Now, in order to fix that, we have to kind of just observe, okay, what was the relationship between tree, subtree y, and 3 and 5? Well, obviously, subtree y is bigger than 3, and it is smaller than y, okay? Because it's smaller than 5 because, well, we get to the subtree y by traversing down the left subtree of 5. So anything on the left side of 5 must be smaller than 5. So that's how we have this relationship here. And using that relationship, we can now actually take the subtree y and just put it on the left side, left child of 5, because 5 now has no left child. So how convenient, right? We can just attach subtree y to the left child of 5. And now if you look at the this original relationship of 3 is smaller than y, which is smaller than 5, that is preserved in the new tree, right? That because uh, y is still bigger than 3, because we get to y by going down on the right side of 3 now, and y is still smaller than 5 because y is on the left hand side, left child of 5. So that's how we're able to do this, and we're again preserving the data, preserving the ordering, but the tree is now more balanced. Now that we work out a general case for single right rotation, as you guessed it, there is a general case for the single left rotation, and this would be an example of a AVL tree that will require a single left rotation. So please try to work this out. Okay, and assuming you've done that, I would hope that you end up with something like this. Okay, so now that we work out the general cases for single left and right rotation, let's work on a real AVL tree that has gone out of balance, and let's try to identify where the imbalance occurs and then try to fix it. Okay, so here is how I approach it. Now, remember there could be nodes with multiple, oh, sorry, there could be multiple nodes with that violate the AVL tree invariant. Now, when we always want to start with the one that is lowest in the tree. So in this case, that turns out to be the node number 8 here. On its left subtree has height of 0, 1, 2. The right subtree has a height of 0. So that's the difference is 2, and that's more than 1. Now, next thing we want to do is identify which case it is. Is it left, left, right, right, or some other cases we'll consider later. Now, in this case, it's left, left because for node 8, the left child, left subtree has a higher height. And then if you go down on the left side, you come to node 5, that also the left child of node 5 has a higher height. So we're going down left, left. And if it's left, left, then what we're doing is we are doing a right rotation. And basically what happens is we take 8, attach it to the right, it becomes the right child of node 5. Node 8 becomes the right child of node 5. And you know, everything else is the same, except obviously we have to do something with the 7 here, but the 7 can become the left child of node 8. Okay, I hope that makes sense. If it does not, you know, just try to stare at this for a little longer, you know, work your magic with paper and pencil, and I think it will eventually make sense. Now, one thing I want to point out is you see these numbers here. These numbers is the height. Now, the this software, and I'll talk about this software in a little bit. this software actually assume the height of the leaf nodes are 1 rather than 0, like what we are doing in this class. Another thing that I want to mention is, yeah, you look at these pictures, I did not draw them. So these pictures are actually generated by a data structure and algorithm visualization tool. I have links to two of these tools. I think the first one is for binary search tree. The second one is for AVL tree. And actually they have a bunch of visualization for other data structures and algorithms as well. So they are useful. They are, study aids. Uh, but it's very, very important that you know how to identify the the imbalance, and how to do the rotation by hand by yourself. Um, uh, this tool is great for visualization on kind of verification of once you've done it by hand, you can use it to verify to make sure you get it right. But these are just tools; they are not substitute uh, for your understanding of how the algorithm works. But they are useful when I need pictures like this and when I need to verify my results.